Hi, my name's Don Tipping, and welcome to the Agrarian Renaissance podcast, where we explore tools and techniques for creating a resilient, regenerative community and stable regions where we look to one another rather than outside ourselves for the solutions to the problems that we face in our lives. I've been practicing permaculture and be an organic farmer for over 30 years now, so I'll be sharing from my own experience of what I've learned that has worked, and I'll also be bringing in guests that are from my local community and the larger global community who have demonstrated excellence and unique insight based on their particular life path of ways that we can look to each other to come together and create a brighter future for ourselves, our families, our region, and the watersheds where we live. Hi, I am Don Tipping, and welcome to episode 7 of the Agrarian Renaissance podcast. And we're picking up where we left off with episode 6, where we were exploring the work of Nikolai Vavilov, the Russian botanist from the previous turn of the century, who developed the largest seed bank in the world. And part of what he discovered in that idea of the centers of origin for our domesticated crops was this idea of photoperiodicity, and that plants adapt to the day length that they experience. Because think, they are solar collectors. Unless it's a heterotroph, that are plants that don't photosynthesize, and they live in an association with mycorrhizal fungi, but I'm pretty sure we don't eat any of those or use any of them besides maybe medicinals. All plants are basically using sunlight and photons to convert it into sugars and to grow their tissues and their flowers and seeds and fruits and however they manifest in the world. So this idea of photoperiodicity is one that I haven't really seen discussed very much, but having had a seed company for quite a number of years, I have begun to include this information of what latitude was it grown at. So here in southwestern Oregon, we're at 42.2 degrees north latitude. So the 45th parallel is basically, that's the halfway point between the equator and the North Pole. And any of you that live here in the Pacific Northwest and you've been driving up to Portland, right before you get to Portland, there's a sign on I-5 that says 45th parallel. And these are lines that if you picture a globe in your mind, you can draw around. And on any good globe will have the latitude lines and longitude lines. And obviously for navigational aid, figuring out some means of demarcation to know where you are is really helpful. And GPS coordinates, for those of you that are familiar with that lens on it, or geotagging or geocaching, are your latitude and longitude coordinates. For today, we're particularly going to delve into latitude, which are the lines, I suppose they're parallel, that go up and down from the poles. The longitude, once again, to rehash, are the ones that connect the poles. We're not going to pay attention to those today. So what an interesting exercise I like to do is first figure out where you are on, what's your latitude. Go and pause the podcast right now, go figure it out, just Google it or look on a globe or a map. And once you have that figured out, and if you have that globe, draw a line and look, where does that line bisect? And for me, interestingly enough, I was born in a suburb outside of Detroit, Michigan, which is exactly at 42.2 degrees north latitude. Totally an ironic coincidence. Keep going across, eventually, we're going off the United States proper and into the ocean. Then that line bisects Portugal, southern Spain, Monaco, right through Italy, through Turkey, near Istanbul, and through northern China and Korea, and through the southern tip of the North Island of Japan, Hokkaido. And if we go around the other way, we've connected up with Japan. Now here's an interesting exercise. Imagine you could do that on the southern hemisphere. So 42.2 degrees north or south latitude goes through Chile, and then I believe Argentina, and it also goes through New Zealand, interestingly enough. So those places basically on the summer solstice, here's a good way to picture it. Summer solstice here, the sun is setting about 9:30. It's light till about 10. Winter solstice, the sun setting about 4:30 or 5. all those places along the line are going to have the same amount of day length, winter, sun. Same in the southern hemisphere. As you go north, you get a little bit longer days in the summer, and anyone who's been in the far north knows that you have midnight sun at the summer solstice in places like Alaska or far northern Norway or Iceland. Same as you go south. Another interesting way to view this is you can go south all the way to the equator where it's 12 hours day, 12 hours night year round, basically. There's no seasonality. So the seasons in the equatorial regions, it's more about dry season, wet season. And being in Kenya recently, where the equator goes right through Kenya, they have what they call the little rains and the big rains, and then dry periods in between. They don't have winter, spring, summer. Those just aren't useful ways to describe things because there isn't any difference. Some crops are highly sensitive to day length. Onions are the classic one, and if you're a gardener, you want to find seeds of what are either called day neutral, meaning you have more flexibility of where you can grow them, or long day or short day onions. So a long day onion, like a Walla Walla, we have a strain called Siskiyou Sweet, works really well in these northern latitudes, where as we approach the summer solstice, we have really long days. And then as the day length begins to shorten, that's when you get bulbing and the plant begins to go into dormancy to get ready for being asleep because it's a biennial. Same with garlic. And really, now's here where this becomes a skeleton key for you to understand agriculture, botany, how plants adapt to their environment, is onions and garlic are both in the lily family, as the actual botanical name would be the Amaryllidaceae. So think of daffodils. You're planting them in the fall, they flower in February, and then come summer solstice, you can't even see them. They've gone dormant. So the highly photoperiodicity sensitive. And some crops much more so than others. One way I learned a profound lesson about this is I was able to bring some corn seeds back from Ecuador, and then somebody else gave me some from Peru. They've got a lot of diversity of corn, as they call it, maize, down there that we don't have here and that you just don't see growing. And if you've ever seen those choclo ears, those big ones where each kernel is like the size of one digit of your thumb. When we grew these, we planted it, we did everything right as far as growing corn, and we can successfully grow some pretty long, large ears of corn that require 100 to 120 days to mature. When we planted these, they grew to be 16 to 20 feet tall, with these huge stalks and roots coming off the stalk 1 foot, 2 foot off the ground. And because these tropical adapted varieties were used to growing where there's 12 hours a day, 12 hours a night. So when we had these days where there's 16, 17 hours of daylight, they're just like, woohoo, let's grow, grow, grow. They got super tall. They didn't make ears or begin to make ears until September, and at which point for us we can get frost and colder temperatures anytime after the fall equinox, typically about mid-October is when we get frost. So we're not able to successfully grow that crop here. If you grew those same seeds in their native habitat in Ecuador, Peru, and the local area of the Andean mountains, they get to be about 6-7 feet tall. They don't get super tall because they're less reliant on a day length trigger to flower. Anyone who's familiar with cannabis, this is, I guess, the elephant in the room, knows that it's highly photosensitive. And there's all these people who cultivate it who actually use a practice where they are using a way to block out the sun to trigger early flowering. They call it light deprivation. And by carefully timing it, they can get it to flower more quickly. And people do that for economic purposes. And there are other varieties. So generally, cannabis requires this, much like the onions or the corn, a period where it's growing vegetation, leaves, and then as the day length begins to shorten, it flowers, and then those flowers mature, ultimately into seed, is what the plant is wanting to do. So, and then there's other strains of cannabis because it's such an old plant with humanity, and it's a little muddy. There's a man who wrote a book called Cannabis Botany. I believe his last name is Clark. I'll put it in the show notes. And he looked that there could be multiple centers of origin for cannabis, and some were naturally day neutral, meaning they were not as affected by day length. And those are the varieties generally grown for fiber and seed in China. and that what we have today is a convergence and a hybrid of these two strains. That's a whole other topic. Maybe I'll bring in an expert about that because it's not my area of expertise. I want to get back to the notion of photoperiodicity, and we'll go back to corn as an example. And corn, the wild ancestor of corn, which the Latin name is Zea mays, M-A-Y-S, even though maize, M-A-I-Z or M-A-I-Z-E, is what people call corn around most of the world except for the U.S. That came from the central Mexican highland regions at an elevation of about 4,000 to 5,000 feet as a wild subtropical grass that was highly sensitive to day length. And it looks like corn. Zea mexicana is the Latin name of that plant. And when we grow it here, the kernel, it doesn't really make a cob. It makes a squiggly aggregation of small, hard, triangular kernels, if you will, along a vestigial cob. And corn is what we call an imperfect flower in botany. Some flowers, like a lily, is a perfect flower. It has both male flower parts, the pollen-producing parts, and the female, the pollen-receiving, the stigma and the ovary, on the same flower, in the same flower. However, corn, if you look at the tassels, the part up top, that's where the pollen's produced. That's the male. And then the silks emerging out of the immature ear, which is the ovary, are the female flowers. So one grain of pollen lands from the tassel on a silk and then grows a pollen tube down that silk to fertilize an ovule. And then that ovule begins to swell. So if you're ever eating sweet corn and you see blanks, if you will, those are basically unfertilized seeds, which is fine. It's not going to do you any harm, but just so you know what was actually taking place there. We'll do a whole episode about corn, maize, just because it's a huge one. In further episodes, we'll do the primary grains of corn, wheat, and rice, just because they represent 70% of the calories consumed globally today, generally speaking. So back to Zea mexicana, teosinte is the one of the indigenous languages. I imagine there was a multitude of the various Mayan dialect and Aztec dialect languages for this plant because it became so important. But if you were to look at teosinte, you wouldn't say like, oh, that looks like good food. And then when we've tried to grow it here, it grows about 8 to 10 feet tall, much like the Andean corns, begins to flower in late in the year, almost to fall, and we barely get seed. I've always wanted to offer it through our seed company, mainly for people who are the botanically curious, and there is interesting anecdotal information among Mayan farmers that they will still allow teosinte as a weed to grow in their corn patches because they have a belief that it strengthens their crop, which there could be some truth there with epigenetics and all that, and we'll unpack that later with somebody that actually knows molecular biology and can speak to it intelligently. So that teosinte, you can see, I made the jump from Mexico to Oregon. The plant, it had one season to adapt. That's not enough time. But think, through indigenous trade routes, and even quite possibly being eaten by birds and other things and moved northward, indigenous farmers moved maize, we'll just call it maize as a wide thing, slowly up the latitudes to where by about 1,000 years ago is the first record of the Apache peoples. There's numerous bands of the Apaches who live in the Arizona border region. They make the claim of they are the ones that brought corn into North America. And you can think of all of those beautiful depictions of Southwest agriculture, the corn, bean, squash, and the melons, and the chilies, and the thunder gods, and it shows up in their beadwork, their weaving, their songs, and it's among the most beautiful intact agrarian. It's like a poem or like an opera or like a classical piece, really. But that took a while to get up there. They believe we domesticated corn, from teosinte like 10,000 years ago. So it took 9,000 years to make it from central Mexico to Arizona. It didn't make it to the Iroquois and the various bands of the Iroquois, which was, I believe, a French name given to those peoples, and they have names like the Haudenosaunee, the Seneca, the Onondaga, the Confederated Tribes of the Iroquois up there. It didn't make it up there till about 1200 AD from what we understand about genetics, which could be wrong. Maybe we'll learn new things. Or no, I'm sorry, not 1200 years ago, 1200 AD. So, it took it about 200-300 years to make it from Arizona to New York, and then eventually it made it up into Saskatchewan and other areas of Canada. But you look at their indigenous corns and they're short. They're 2-3 feet tall because they just have the short season. They can't wait for the plant to grow this big tall stalk. It just grows a shorter stalk, and then it makes corn that works for them. And I'll put a link in the show notes to Winona LaDuke has an excellent TED Talk where she unpacks some of her own Ojibwe heritage as it relates to corn, maize specifically. And it helps you understand that journey of how long it took to adapt. And you really only get one growing season. Maybe in Mexico you got two. So one growing season. So it took centuries for the plant to, the ones that were actually able to make seed. Let's say through trade routes, somebody got a bag of seed and they took it from Arizona up to Wyoming. Let's just say Wyoming. They planted it. I bet it grew, but then a frost came in, early September and wiped it out. It didn't make seed, so it never had an opportunity to adapt there. And as one of my plant breeding and seed growing mentors, Dr. John Navazio, the late great John Navazio, said, when you get a pollination, we say, we want to protect the pollinators. Like the pollinators are really important. Pollination is recreation. There's a lot of pollen getting thrown out there, and the pollinators are not trying to affect pollination. Pollination is the moment the grain of pollen lands on the stigmatic surface and it germinates, which is an interesting thought. So it's not a seed, it's pollen, it germinates. And then it grows a pollen tube down into the ovary of the plant, which in the case of like a bean is a bean pod, and in the case of a squash, it is the fruit. So the seeds are encased in an ovary. So when you eat a tomato or a cucumber or a squash, you're eating an ovary, botanically speaking. Pollination is recreation, back to what Navazio said, but fertilization is procreation. So if you have a difficult weather event, as that pollen tube is growing, it can arrest fertilization. And pollination is happening all the time in nature, but those fertilization attempts are a successful fertilization is where a viable seed can be formed, which is an opportunity for adaptation. And this idea of the plant adapting to the light conditions, the latitude, the seasonality of the environment, and then for that genetic information from the male and the female and all its progeny to move forward one more generation. And so when you think how every living thing, plant, animal, mushroom, fern, horsetail, lichen, moss, is the result of this just slow, sequential adaptation to its environment. And this was a big aha moment, and I'll close here. There'll be a future episode about Darwin and evolution specifically because I had a lot of aha moments. But I used to think evolution was, the next version's always better. Like you get the iPhone, you're like, the next iPhone's just going to be better. And then you realize they put weird malware in it where it begins to corrupt. It's not as good. I want the old one. It was more sturdy. So likewise with evolution, all evolution is the ones that did well in that growing environment, that got to survive. And then they get to mate and be the next generation. And evolution can move backwards. Think of our little pinky toes. They're not long for this world unless we start earthing and going barefoot a whole lot more. We don't need them. So it's interesting to look as you go out there from this. Now put your phone down or your computer and go outside if you can, if it's not too dark, and just consider everywhere you look, everything you touch, everything you breathe in is all the result of this just slow dialogue with nature, sunlight, water, the pests, the diseases. It's too big to really fathom, but if you take one thing, and I'll close with this last thing. Everybody knows Darwin from his trip to the Galapagos and the turtles and all this stuff. But Darwin left a place of his lawn unmowed 30 years, 40 years. I can't remember which one it is. And he took notes of the species composition in that area of unmown lawn. And he was a bit of, higher class person. So I'm sure his neighbors were like, dude, mow your lawn, graze your lawn, get out there with the scythe, keep it trim and tidy. He learned as much information from the species evolution of decades of lawn and the thistles and the brambles and the small trees as he did as going to the Galapagos. It's everywhere you look. You don't need to go to the rainforest to learn about nature. You could look at the smallest patch of earth. And that's, again, consider the day length, find a spot and track how the sun moves. This time of year, it begins to move really quickly as we move to the fall equinox. And I noticed the sun hitting new areas. I'm like, wow, that's different, because it moves closer in the north or the south to the equinoxes than at the solstices. So it's rapid right now. So that idea of periodicity of solar cycles. And I really hope that you were able to learn something from that today, and definitely check us out and share this podcast with friends that you think might be interested in it, or drop us a message with suggestions of topics or people that we may want to interview in the future. Thanks so much. Take care.